Solar energy is clean, but it has a major flaw: intermittency. Because the Earth rotates, our solar panels only work during the day. Notice the pattern. Solar power output peaks at noon, but drops to zero at night. This duck curve makes relying solely on solar for baseload power very difficult. Beyond the day-night cycle, clouds and atmospheric conditions block sunlight unpredictably. These factors limit solar to a low capacity factor. To solve this, we look above the atmosphere. Orbital Solar Mirror Arrays, or OSMA, can act as a space-based spotlight, redirecting sunlight to the ground even after the sun has set. Welcome. Today we are looking at something truly visionary: the Orbital Solar Mirror Array, or OSMA. Think of an OSMA not just as a satellite, but as a giant, precision-engineered cosmic spotlight. It is a constellation of satellites equipped with ultra-thin parabolic mirrors. These mirrors are designed to capture sunlight high above the clouds and reflect it back down, focusing the light onto terrestrial photovoltaic arrays here on Earth. By working as a coordinated constellation, these mirrors ensure that energy is available even when the local sun has set, acting as a bridge to constant power. This system turns the vacuum of space into a powerful tool for terrestrial energy, redefining how we capture sunlight. To focus sunlight from 500 kilometers away onto a small target, our orbital mirror needs a precise parabolic curve. This shape ensures that all parallel rays of light converge at a single focal point. Mathematically, we use the mirror equation to calculate this focus. The focal length is determined by the satellite's altitude and the desired size of the light spot on the ground. Remember, precise curvature means precise energy delivery. By adjusting the mirror's geometry based on these calculations, we turn the vastness of space into a reliable solar power source. Why do we use a parabola for our orbital mirrors? It is all about the geometry of light. Incoming sunlight travels in parallel rays. A parabolic shape is mathematically perfect at reflecting every one of these rays toward a single, shared focal point. In space, we achieve sub-millimeter precision through electromagnetic tensioning. This active system keeps the mirror surface perfectly shaped, even while moving at high speeds. By maintaining this exact geometry, we turn a vast orbital mirror into a highly efficient energy collector. Imagine trying to hit a target the size of a single city block from 500 kilometers in space. This is the 1,000-mile sniper challenge. Even the smallest change in the mirror's tilt, measured in micro-radians, can cause our light beam to miss the target by miles. Precision is vital. The mirror requires micro-radian accuracy. A micro-radian is a tiny angular measure, equivalent to the width of a human hair viewed from 100 meters away. To ensure our solar mirrors keep the light focused, these systems use active feedback to hold this extreme precision constantly. Stability is the secret to delivering clean solar power from orbit. To keep our solar mirror locked onto a target, we rely on the physics of orbital mechanics. These satellites travel at thousands of miles per hour. We place them in what is called a sun-synchronous orbit. This special path allows the satellite's movement to stay coordinated with Earth's rotation. By matching the orbit correctly, the mirror can keep its light beam focused on the exact same spot on the ground, regardless of how fast the Earth is spinning below. The takeaway: orbital mechanics transforms a moving satellite into a fixed, stationary power source for our terrestrial grids. Space is a perfect vacuum, where light travels in a perfectly straight, predictable line. However, Earth's atmosphere is dense. It has a higher refractive index than the vacuum of space. When our solar beam hits the air, the change in medium forces the light to bend, a process known as refraction. This deviation means our target on the ground is not exactly where the straight line from space would suggest. We must mathematically calculate this shift to ensure our solar energy hits the target every single time. Light travels in a straight line through the vacuum of space, where the refractive index is essentially 1. However, as it hits our atmosphere, the density changes, causing the light to refract. We use a modified Snell's law to calculate this. The atmosphere acts like a lens. To hit our target on the ground, the orbital mirror must precisely tilt to compensate for this bending effect. By adjusting the mirror's angle based on the refractive index of the troposphere, we maintain perfect focus on our target. When a high-intensity solar beam passes through the atmosphere, it isn't just traveling through empty space. It deposits energy as heat. This heating causes air molecules to vibrate faster and spread out. This creates a pocket of lower density air in the path of the beam. Because the air density has changed, the refractive index changes too. The pocket of hot air acts like a diverging lens, bending the light outwards. We call this phenomenon thermal blooming. It scatters our precision beam, reducing the energy reaching our solar grid. Understanding this heat-induced distortion is critical for our orbital math. Active wavefront correction is the secret to perfect energy delivery. Think of the atmosphere as a funhouse mirror that distorts light rays. Without correction, these rays hit the ground scattered and weak. This is due to temperature differences creating turbulent air cells. Our orbital mirrors use AI to predict this distortion. The mirror surface vibrates in real time to pre-distort the light. By sending this pre-distorted beam, the atmosphere naturally straightens it out as it passes through. The result is a perfect focused beam on our target. This constant AI feedback loop keeps our energy delivery at peak efficiency, regardless of weather conditions. As sunlight enters our atmosphere, tiny molecules scatter shorter wavelengths, like blue light, in every direction. This is Rayleigh scattering. This scattering steals energy from our power beam. To fix this, our orbital mirrors are coded to reflect only specific, longer wavelengths that penetrate the air with minimal interference. To ensure reliable solar power, we need high beam coherence. This basically means keeping all the light waves perfectly aligned as they travel through space and air. When our solar beam hits the atmosphere, clouds and turbulence tend to scatter the light, causing it to lose its focus. But here is the clever part. Our systems use rapid feedback loops that communicate 1,000 times per second to reshape the beam. This constant correction allows us to maintain 98% coherence, essentially turning overcast conditions into high-yield solar hours. To maintain a steady beam, the orbital mirror and ground station engage in a lightning-fast feedback loop. Ground sensors constantly monitor the beam's position, communicating with the satellite 1,000 times per second. If atmospheric turbulence shifts the light, the system detects this deviation instantly. The mirror tilts in real time, correcting its angle to keep the energy locked perfectly on the grid. This constant adjustment ensures that even through turbulent air, the solar energy stays precisely focused. A single mirror can't provide 24/7 power because it eventually moves out of position. To solve this, we use a sun-sync constellation. By placing satellites in a precise chain, as one mirror moves out of the optimal viewing angle, the next one seamlessly takes over. This constant handover ensures that the target location on Earth receives continuous, uninterrupted solar illumination. It's like a relay race where the baton of sunlight is passed continuously, providing a stable, reliable energy source regardless of where the Earth is in its rotation. We often rely on complex conversion chains to get power to the grid. In many systems, sunlight is first converted to electricity, then into microwaves, and then back to electricity. Each of these steps results in energy loss. It is a thermodynamic tax that lowers our overall efficiency. A better approach is direct light concentration. By beaming sunlight directly onto high-efficiency panels, we skip the intermediate steps entirely. This keeps energy density high, ensuring that more of the sun's original power reaches our terrestrial systems for conversion. It is cleaner, faster, and more efficient. Project Helios Sync in the Atacama Desert served as our critical proof of concept for orbital solar mirrors. This pilot project was designed to demonstrate that we can reliably deliver concentrated sunlight from space to a specific ground location. The results were remarkable. The system maintained a concentrated light spot just 15 meters in diameter. Even more impressive was the control system, which kept the beam steady with less than 2% jitter, proving our aiming precision. This isn't just about peaking energy during the day. By successfully managing this beam, we proved that orbital mirrors can provide true baseload power. This allows us to deliver energy reliably, transcending the limitations of traditional solar intermittency. Think of capacity factor as a power plant's uptime. It measures how much energy a plant actually produces compared to its absolute maximum potential if it ran perfectly at full power 24/7. Traditional solar panels are limited. They only produce power during the day and are often throttled by clouds. This leaves us with a capacity factor of just about 20%. By using orbital solar mirrors, we can direct sunlight onto terrestrial grids continuously. This pushes our capacity factor up to 85 or 90%. This finally makes solar energy as steady and reliable as traditional nuclear or coal-fired power plants. The key takeaway is reliability. With OSMA, we aren't just capturing sunlight, we are creating a consistent baseload energy source that overcomes the intermittency of the traditional solar model. When we talk about directing solar power from space, safety is our absolute top priority. The system is built with a sophisticated fail-safe tracking mechanism. If the signal is lost, or if the mirror begins to drift even slightly off target, the system responds instantly. The mirror tilts away from the target in milliseconds, ensuring the beam never touches unintended areas. This keeps the environment and surrounding infrastructure completely safe. By relying on real-time feedback loops, we maintain a precise and environmentally responsible energy delivery system that respects the Earth below. We have covered a lot today. Let us summarize the key takeaways of our look at orbital solar mirror arrays. First, we use orbital mechanics to achieve persistence, effectively eliminating solar intermittency. Second, we apply the physics of Snell's law to manage light refraction across the atmosphere. And finally, AI-driven adaptive optics allow us to maintain 98% beam coherence for reliable power delivery. By combining these technologies, we are turning space into our most reliable power station. We are effectively turning off the night for our solar grids. By redirecting the sun's energy from orbit, we aren't just changing how we produce power, but fundamentally optimizing our relationship with our star. The future of energy is quite literally looking up.